Hello and welcome to New England Dynamics and Numbers Theory Seminar. Today we have Carsten Peterson, who is joining us from Europe, and the talk is about quantum ergodicity of the Bruhat-Tits building for PGL3 in the Benjamini-Schramm limit. Lots of interesting words. I hope you'll explain it all.
Yes, thank you, and thank you for this opportunity to talk about my work. Yeah, there are a lot of potentially exotic words in the title, but I hope to explain what all of these words mean. So let me start with something that's probably more familiar to this audience, which is the geodesic flow on a hyperbolic surface. So suppose you have a compact hyperbolic surface, and then on the unit tangent bundle of this, you have the geodesic flow, which is simply defined as follows, given a point and a direction that defines for you a geodesic, and you simply move that point and direction along that geodesic for time t, and you see what point and direction you end up at. But because hyperbolic surfaces have negative curvature, this dynamical system will be ergodic, which in particular implies that if you take a generic point and direction and you move along the associated geodesic, in the long run, you'll be equally likely to end up everywhere on the manifold. So there's a sense in which you can think that the geodesic flow is something like a classical mechanics on a manifold, because classical mechanics is, says if you don't have external forces, then classical particles will travel in straight lines at constant velocities, but a straight line moving on a straight line at a constant velocity in a curved space is exactly moving along a geodesic. And then it's natural then to ask, what would the analog of quantum mechanics be? Well, usually quantum mechanics is concerned with solving the Schrödinger equation, which tells you how to evolve some kind of L2 function on your manifold. But the Schrödinger equation involves, it involves the Laplacian, which we'll see a lot in this talk. And it also involves this parameter h, Planck's constant, which mathematically, or which physically is an actual number, but mathematically we can treat it as just some small parameter. And there's a mathematical procedure for moving between this classical mechanical world and this quantum mechanical world called quantization, using tools from microlocal analysis and semi-classical analysis. And there's actually kind of, at least heuristically, you expect to kind of be able to go backwards, namely, in this quantization procedure, h is just some variable that we can set to be whatever we want, and you expect that in the limit as h goes to 0, quantum mechanics should kind of devolve back into classical mechanics, and in some sense, that's what motivates the original quantum ergodicity theorem. So let me tell you how to interpret quantum particles on manifolds. So let's just renormalize our volume measure to be total volume 1. A quantum particle is modeled by an L2 function with L2 norm 1, namely its wave function, call that psi. And quantum particles do not have definite positions, but you can say, if I look for the particle in some region E, how likely am I to observe it there? Well, that's given by integrating the norm squared of the wave function over that region E. But on the other hand, ergodicity is concerned with some kind of equidistribution properties of essentially classical particles on the manifold. So what would it mean for a quantum particle to be equidistributed? It should mean that the probability of observing your particle in some region of the manifold is just directly proportional to the volume of that region. And we'll see that quantum ergodicity is concerned with measuring the difference between these two types of expressions, which basically measures, in some sense, how far from equidistributed your quantum particle is. So let me also remind you some facts about the Laplacian. On a compact manifold, the Laplacian will have discrete L2 spectrum. So you'll get an orthonormal basis of eigenfunctions, and all the eigenvalues will be non-negative. They'll only accumulate at infinity. And then in this quantum mechanical framework, you can interpret an eigenfunction of the Laplacian as a quantum particle that has a definite energy, which is equal to its eigenvalue times h squared. But for us, h is just some parameter that we can play around with. So what if we let lambda j go to infinity, but along the way, we keep rescaling h in a way that makes this expression h squared lambda j of constant size 1? Then we have this kind of dual interpretation that letting lambda j go to infinity is analogous to fixing energy to be of size 1 and letting h go to 0. But letting h go to 0, at least heuristically, somehow we should recover classical mechanical phenomenon from quantum mechanical phenomenon. So if the underlying dynamical system is ergodic, we should somehow recover this in such a limit, which is to say that these quantum particles should, quote unquote, equidistribute. And that's really what quantum ergodicity is about. So this is one version of the quantum ergodicity theorem, and it's due to various people in various levels of generality, Sneelman, Zeldich, and Colleen de Verdier. So suppose you take a test function, A, and you should really think of A as something like a smooth approximation to like an indicator function of a region. Then for each lambda, you're going to average over all eigenfunctions with eigenvalue less than lambda. And then you basically want to compare the measures psi j squared dvol and the uniform measure. And you're going to compare these by integrating against the test function. And like on the previous slide, our test function was something like the indicator function of a region. So this would be like measuring the discrepancy between how likely you are to observe a particle in a given region versus the size, the volume of that region. And what the theorem says is that in the limit, this expression is equal to 0. And this sort of expression that's showing up in the sum, this difference between these integrals, as often I'll refer to that as the quantum variance. But we can interpret this theorem as saying that, on the one hand, you could interpret it as saying generic high energy quantum particles equidistribute, or generic bounded energy quantum particles equidistribute, and the limit as h goes to 0. Okay, so the type of quantum ergodicity that I'm going to be concerned with is actually going to be a slightly different framework. So just as a reminder, the eigenvalues of the Laplacian lie in this interval 0 to infinity. And in the theorem I just described, you could think of the framework as follows. You fixed some hyperbolic surface, and then I average this quantum variance expression for eigenfunctions with eigenvalue in this window 0 to lambda, and I let my window 0 to lambda grow to infinity. But the sort of limiting procedure I want to consider is different. So now, instead of taking just one manifold, I want to consider a sequence of manifolds, say a sequence of hyperbolic surfaces, which in some sense converge to the hyperbolic plane. And then I'm going to fix once and for all a spectral window, compact spectral window. And for reasons I'll explain in a minute, I want this window to lie above 1/4. And then I'm going to average this quantum variance type expression just over the eigenfunctions with eigenvalue in this window. But what do I mean by a sequence of hyperbolic surfaces converging to the hyperbolic plane? This is made precise by this notion of Benjamini-Schramm convergence. So we'll say that a sequence of hyperbolic surfaces, Benjamini-Schramm converges to the hyperbolic plane if, for every choice of R, the proportion of points whose injectivity radius is less than R is equal to 0 in the limit. And just as a reminder, the injectivity radius of a point is just the size of the biggest ball you can embed around that point before the ball starts to wrap back up on itself. So we can interpret Benjamini-Schramm convergence as saying that asymptotically, most points have arbitrarily large injectivity radius. And a good example to keep in mind would be a tower of covers of a fixed hyperbolic surface where maybe the global injectivity radius is going to infinity. But this type of convergence is weaker than requiring that the global injectivity radius go to infinity. You just basically require that for most points, the injectivity radius goes to infinity. And it also makes sense that if we are considering spectral questions for sequences of objects that are converging to the hyperbolic plane, well, then the spectrum of the hyperbolic plane itself will play a distinguished role. And the spectrum of the Laplacian on the hyperbolic plane is the region 1/4 to infinity as opposed to the region 0 to infinity, which explains the appearance of 1/4 on the previous slide.
And are your surfaces are compact?
Yeah, these are compact. Yeah.
So technically you can have cusps and also converge, right? So,
you can, but for what I'm describing, I'm assuming compact.
Okay.
Yeah. Although there are results in the cusp case as well, but yeah, I just want to talk about compact today. So here is a theorem due to Lemeson and Solston concerning Benjamini-Schramm convergence sequences of hyperbolic surfaces. So suppose you take a sequence of compact hyperbolic surfaces which Benjamini-Schramm converge to the hyperbolic plane. And assume that you have a universal lower bound on the second smallest eigenvalue, bounded away from 0. So you always have 0 as an eigenvalue, but I want that the second smallest eigenvalue is uniformly bounded away from 0. And I also want a global lower bound on the global injectivity radius for all of these surfaces, that it's bounded away from 0. And now I consider the eigendata for each one of these surfaces. So I get an orthonormal basis of eigenfunctions, and I'm going to use this indexing where this upper index n is keeping track of which surface I'm talking about, and this lower index j is keeping track of the pairing between the eigenvalues and the eigenfunctions. And I'm going to fix once and for all a compact subinterval I, and I want this interval to lie in the region 1/4 to infinity. For each surface, I'm going to choose a test function, and the only thing I'm going to assume about how these test functions relate to each other for different surfaces is the uniform L infinity bound. And then in the theorem, what you're going to do is average over all eigenfunctions with eigenvalue in this region I, and then you're going to measure this quantum variance expression, which is some weak way of measuring how far from equidistributed your eigenfunctions are. And the theorem says that in the limit, this expression is 0. So now I want to point us in the direction that I ultimately want to end up, which is these Bruhat-Tits buildings. So these hyperbolic surfaces are examples of rank 1 locally symmetric spaces. And in the background is the real Lie group, semi-simple Lie group SL2R. And more generally, you can construct geometric spaces from semi-simple real Lie groups, and these spaces are called symmetric spaces. But there's a completely parallel theory when you work with algebraic groups over non-Archimedean local fields, say like over the p-adics. And really the analog of a hyperbolic surface in this context would actually be a regular graph. And I'll explain this analogy further in the following slides. And then in general, the analog of these symmetric spaces are these infinite simplicial complexes you can construct from the group called Bruhat-Tits buildings. And so in the following slides, I want to explain all these analogies between symmetric spaces and buildings, Bruhat-Tits buildings. But first, I want to say something about how quantum ergodicity is going to work in higher rank. So first off, the rank of a space, it has an algebraic definition, but geometrically it corresponds to the dimension of the biggest flat subspace that you can embed in your space. And in rank 1, such as for a hyperbolic surface, the geodesic flow is ergodic, and we saw that quantum ergodicity involves studying eigenfunctions of a single operator, namely the Laplacian. But in higher rank, the geodesic flow is in fact never ergodic, but there's a natural ergodic RK action on some natural bundle over the locally symmetric space, and this flow is called the Weil chamber flow or the Cartan flow. And it's really sort of this flow that we want to quantize in this sort of quantum ergodicity. And because this is an RK action instead of an R action, quantum ergodicity will involve studying K operators instead of just one operator. So now I want to explain some of the basic theory of symmetric spaces, and I really want to highlight the analogies between symmetric spaces and Bruhat-Tits buildings. So the framework for symmetric spaces, you start with a semi-simple real Lie group, and I'm really interested in the symmetric spaces of non-compact type, so we'll assume that this Lie group doesn't have any compact factors. Then you can construct from that an associated Riemannian manifold of non-positive curvature called a symmetric space. And when you do this for SL2R, you get a hyperbolic plane. And this group G will act by isometries and transitively on X, which will allow us to realize the symmetric space as a homogeneous space for the group G. Namely, it's this space G mod K, where K is a maximal compact subgroup. And then on this space, we can consider the algebra of all differential operators that commute with the group action. And it turns out that in rank 1, this algebra is exactly the algebra generated by the Laplacian, or it's really basically polynomial expressions in the Laplacian. But more generally, the structure of this algebra is specified by something called the Harish-Chandra isomorphism, which in particular tells you that it's a commutative algebra generated by K operators if K is the rank. And I want to point out that the Laplacian geometrically can be interpreted as sort of like an infinitesimal version of averaging over small spheres. And we'll see that in the non-Archimedean setting, it's really the average, sort of averaging over spheres that will play the role of these invariant differential operators. So now I want to tell a parallel story in the non-Archimedean setting. So here you can start with a semi-simple algebraic group over a non-Archimedean local field, such as the group PGL2QP. Then you can construct from this a infinite simplicial complex called a Bruhat-Tits building. And when you do this construction for PGL2QP, the object you get is the infinite p+1 regular tree. And this group G will act by simplicial automorphisms on this simplicial complex, and it will act almost transitively on the vertices. It will sort of act transitively on a finite index subset of the vertices. And when you work with PGLN, it will actually act transitively on the vertices. So roughly speaking, you can realize the vertices of the building as this coset space G mod K, where K is a certain type of maximal compact subgroup. Now, there's a certain algebra of operators that I want to consider on this space that's essentially defined as follows. You want to consider operators acting on functions of vertices of the building that commute with the group action. And this algebra of operators has a name. It's called the spherical Hecke algebra. And it turns out that the spherical Hecke algebra in the case of the tree is simply the algebra generated by the adjacency operator on the tree. It's basically polynomial expressions in the adjacency operator. And more generally, there's something called the Satake isomorphism that tells you the structure of this algebra. And in particular, it tells you that it's a commutative algebra generated by K operators. So as a reminder, the adjacency operator on a tree is defined as follows. If you have a function on the vertices of the tree, then its image under the adjacency operator, the value at, say, this green vertex would simply be the sum of the value of the function at all of its neighbors. So it really is just averaging or summing up over a sphere of radius 1. So let me say something about the geometry of these buildings, which might be a little bit exotic if you've never seen them before. So kind of the building block of a building is what's called an apartment. And when you work the tree, these apartments are simply bi-infinite geodesics. And kind of what's important is that these bi-infinite geodesics in the tree, I can think of them as tessellated copies of R. And somehow the entire tree can be thought of as taking a bunch of copies of this tessellated copy of R and gluing them together with branching along these vertices. And it's really this gluing with branching that's giving the tree negative curvature. And in higher rank, again, the building block is something called an apartment, which is a tessellated copy of a Euclidean space. So PGL3 is a rank 2 group. So the apartments are going to be tessellated copies of R2. And in fact, it will be exactly this type of tessellated copy of R2. And then the entire building can be constructed by taking a bunch of copies of this apartment and gluing them together along hyperplanes with branching. And I kind of do this procedure repeatedly, and I end up with this really non-positively curved object that I can't really draw accurately, and that's what the building is. And what about this spherical Hecke algebra? How can you think about that? Well, on the one hand, you can think that the simplicial complex, I can consider its one skeleton, and I can consider just the adjacency operator on the one skeleton. And that would provide an example of an element in the spherical Hecke algebra. But it turns out that there's more refined adjacency information that's preserved by the group action, and I want to take that into account when defining these elements in the spherical Hecke algebra. So for example, this green vertex, I have a vertex in the building, and I consider all of its neighbors. And it will have, for example, these 6 neighbors, but it will have a bunch of neighbors that are out of the page. I can't really draw them. But it turns out that the neighbors will be come in kind of one of 2 types. And one way to think about it is that, for example, all of these red vertices, and there's also a bunch of red vertices out of the page, they all lie in the same orbit under the stabilizer of the green vertex. And similarly, all these blue vertices lie in the same orbit under the stabilizer of this green vertex. So I could define operators just by saying sum up over all of the red neighbors or sum up over all of the blue neighbors. And it turns out that those two operators will actually generate the spherical Hecke algebra. They'll commute with each other. And we can see, for example, that their sum is just the adjacency operator on the one skeleton. I'm ultimately going to be interested in quotients of these spaces. So suppose that you have a co-compact torsion-free lattice in G, and here G could be either a real or a p-adic Lie group. And then this double coset space G mod K mod gamma, on the one hand, in the Archimedean setting, it's what's called a locally symmetric space, such as a hyperbolic surface. And in the non-Archimedean setting, it's some finite simplicial complex, for example, a finite regular graph. And in both cases, the building and the symmetric space, they're actually contractible spaces because they're non-positively curved spaces. So they are the universal cover for any such quotient by a lattice. And I want to set up a language that will allow me to talk about both settings simultaneously. So I'm going to let C denote as appropriate either this algebra of invariant differential operators on a symmetric space or this spherical Hecke algebra on a Bruhat-Tits building. And I mentioned that in both cases, this algebra is commutative and it's generated by K operators if K is the rank. And then this algebra of operators will actually act on L2 functions on any quotient of my space G mod K by a lattice, and it will actually act by a collection of commuting normal operators, which means that they're simultaneously diagonalizable by an orthonormal basis. So I'll get a decomposition into joint eigenspaces. And I want to record the data of the eigenvalue for each one of my K generating operators of this algebra. I'll record that in a K tuple. I'll call that the spectral parameter. So abstractly, if I have this, I just consider this algebra C as some object, and I want to study the irreducible representations of this commutative algebra. They'll all be one-dimensional, and they'll basically just be specified by some K tuple of numbers by specifying where each of the K generators gets sent. But when I consider the action of this algebra on L2 of the universal cover, so of the symmetric space or the building, not all possible spectral parameters will show up. Only certain ones will show up, and the ones that show up are called the tempered spectrum. And from a representation theoretic perspective, studying representations of this algebra C is essentially equivalent to studying what are called spherical representations. And the tempered spectrum corresponds to the spherical representations that show up weakly in the regular representation. But this is not so important for what I'm ultimately going to describe, but just that this stuff connects with a lot of representation theoretic ideas. We've already seen one instance of the tempered spectrum, because as I mentioned before, when you consider the Laplacian on the hyperbolic plane, you get the region 1/4 to infinity, which is to be contrasted with the region 0 to infinity, which is the collection of all possible eigenvalues of the Laplacian on arbitrary hyperbolic surfaces. And similarly, when you consider the adjacency operator on the q+1 regular tree, the tempered spectrum corresponds to the interval -2 root q to 2 root q, which is to be contrasted with this region -q+1 to q+1, which is kind of all possible eigenvalues of the adjacency operator on q+1 regular graphs. Okay, so something that people have studied, historically has actually been studied for quite some time, although maybe not in this modern language, is if you take a sequence of regular graphs that Benjamin-Ishram converge to the tree, what happens to the distribution of eigenvalues in such a limit? And there's something called the Keston-McKay law that says that the distribution of eigenvalues converges to some limiting distribution called the Plancherel measure, or in that case, it's often just called the Keston-McKay law. And this is a measure that's supported on the tempered spectrum. But really, this is quite a general phenomenon that if you take, so both in the setting of symmetric spaces and buildings and quotients by lattices, if you take a Benjamin-Ishram convergent sequence and you look at the distribution of spectral parameters under such a limit, that distribution will converge to some measure supported on the tempered spectrum. It's called the Plancherel measure. As you can guess, it's the same Plancherel measure that shows up in representation theory. And you can think that the quantum ergodicity in the Benjamin-Ishram limit is really trying to extend these questions where instead of just investigating the behavior of the distribution of eigenvalues under Benjamin-Schramm convergence, you want to investigate the behavior of the eigenfunctions themselves under Benjamin-Schramm convergence. So now I want to take as a model this Laplacian-Salson result I stated previously, and I want to modify it to create a template for quantum ergodicity in the Benjamin-Schramm limit, and it kind of works equally well in the setting of symmetric spaces and Bruhat-Tits buildings. So what I'm about to present is not a theorem, but rather a template for theorems. So instead of considering quotients of the hyperbolic plane, we'll consider quotients of G mod K, so either the symmetric space or the Bruhat-Tits building, by co-compact torsion-free lattices. And we'll assume that this sequence Benjamin-Schramm converges to its universal cover. We'll assume that we have a uniform spectral gap for the action of this algebra C, namely the invariant differential operators on the symmetric space or the spherical Hecke algebra on a Bruhat-Tits building. We'll have this uniform discreteness assumption again. For each space Yn, we get an associated orthonormal basis of joint eigenfunctions of this algebra C, and each eigenfunction has an associated spectral parameter nu. We're going to choose a subset of the tempered spectrum, which is nice, and I'll say more about what nice means later on. We're going to choose a test function for each space with a uniform L-infinity bound, and then what we would hope to prove is that if we average over eigenfunctions with spectral parameter in the set theta, we measure this quantum variance expression, which is some weak way of measuring how equidistributed these eigenfunctions are. We want that in the limit, this expression goes to 0. So this template for theorems results in actual theorems in many cases. And the presentation I gave is slightly ahistorical because the first instance of this theorem was actually in the case of regular graphs, although I used this Laplacian and Salson result to motivate this framework. So Anantharman and Laplacian, they wanted to incorporate quantum ergodicity ideas into the setting of graphs, finite graphs, but it doesn't make sense to take a large eigenvalue limit for finite graphs because they only have finitely many eigenvalues. So they were looking for other natural limit procedures that they could apply these quantum ergodicity ideas to. And so they were the first ones to set up this quantum ergodicity in the Benjamin-Schramm limit framework, and they proved it in the context of regular graphs, which kind of post facto we can interpret as basically rank 1 p-adic locally symmetric spaces, but that's not how they thought about it. Shortly afterwards, a new proof of this theorem was given by Brooks, Laplacian, and Lindenstrauss using a different technique, and their technique used some kind of wave propagation on regular graphs, regular trees. And it's this wave propagation technique that's been used in all of the subsequent results of this form in homogeneous settings. So I already mentioned this Laplacian and Salson result. They were inspired by these earlier results, and they proved this theorem in the context of hyperbolic surfaces using this wave propagator method. And also in their analysis, they used something called the Navier-ergodic theorem. So they were using some actual dynamical ideas. And actually, all of the subsequent results also use this Navier-ergodic theorem, including my own. Then Aber, Bergeron, and Laplacian extended these results to all rank 1 locally symmetric spaces. And in the same paper, they established a joint framework for thinking about the original quantum ergodicity theorem, namely this large eigenvalue limit, and the quantum ergodicity in the Benjamin-Schramm limit. They explained how they can be viewed as special cases of a more general natural limiting procedure for investigating quantum ergodicity. Then more recently, Bromley and Motz investigated these questions for locally symmetric spaces associated to SLDR. They were the first ones to investigate these questions in higher rank. And as you can imagine, moving to higher rank introduces a lot of new technical difficulties. They were able to get around a lot of these difficulties by using so-called polytopo balls, which I will say more about later on. And I also use polytopo balls. But my result is essentially proving the analog of all of these results in the context of the Bruhat-Tits building for PGL3 over a non-Archimedean local field of arbitrary characteristics, so characteristic 0 or positive characteristic. And I build on all of these earlier techniques, but the place where I think I introduced the most new ideas is at a certain step in the analysis that I call the geometric bound, that I'll say more about later on, where you have to essentially bound the volume of a sort of complicated set in the building. So in the last part of the talk, I'll explain more about the wave propagator and polytopic balls and so on. So I just want to point out now that the way that the evolution of ideas happened was first this quantum ergodicity in the Benjamin-Schramm limit was investigated for regular graphs, which after the fact we can interpret as rank 1 non-Archimedean locally symmetric spaces. And this inspired these questions in hyperbolic surfaces and other rank 1 locally symmetric spaces, which then inspired higher rank locally symmetric spaces, which then inspired me to investigate this in higher rank non-Archimedean setting. Let me state my main theorem. So suppose you're working with the Bruhat-Tits building associated to PGL3F, where F is a non-Archimedean local field of arbitrary characteristic. And you take a sequence of co-compact torsion-free lattices, and you have the same assumptions as before. You want that the sequence Benjamin-Schramm converges to the building itself. You want a uniform spectral gap for the action of the spherical Hecke algebra. You want uniform discreteness. For each space, you have an orthonormal basis of eigenfunctions, and they have associated spectral parameters. You're going to choose a subset of the tempered spectrum that is compact and has positive Poincare measure. And you also have the slightly technical assumption that you do not intersect codimension 1 locus, psi. And I don't think that this assumption is strictly necessary, but the analysis gets quite messy on this locus. And in a couple of slides, I'll actually show a picture of the tempered spectrum and this exceptional locus. Then you're going to choose a test function for each yn with a uniform L-infinity bound. And again, there's another technical assumption that this test function be orthogonal to so-called coloring eigenfunctions, which I'll say more about in a minute. But this assumption about orthogonality to coloring eigenfunctions is also can be removed if you add in extra conditions about your orthonormal basis, because the theorem as stated is about any orthonormal basis, but if you have some multiplicity of an eigenspace, then there's some ambiguity about how you choose your orthonormal basis. So if you add in extra conditions, you can get rid of this orthogonal to coloring eigenfunctions assumption. Then the theorem is just as before. You average over eigenfunctions with spectral parameter and some window theta, and you measure this quantum variance, and you show that in the limit this expression goes to 0. And really, in all of these types of results, the right-hand side, you have some bound that goes to 0 under the assumption of Benjamin-Schramm convergence. And I want to point out that actually in this higher rank non-Archimedean setting, several of these assumptions are not necessary. So for example, if you assume you have a lattice and it's torsion-free, then it's automatically co-compact. So you don't need to assume that it's co-compact. That's a non-Archimedean phenomenon. This Benjamin-Schramm convergence assumption can actually be weakened just to the assumption that the volume of Yn goes to infinity. This is due to work of Lander-Levitt. This uniform spectral gap assumption will just be automatic in higher rank because of property T. The uniform discreteness assumption will just follow because of some non-Archimedean compact open phenomenon. Just the discreteness of the building itself will imply this uniform discreteness assumption. Okay, so now let me explain what these coloring eigenfunctions are. So the Bruhat-Tits building for PGL3 has a natural 3 coloring of the vertices. And if you have a lattice acting on the space, sometimes this lattice preserves the coloring and sometimes it doesn't. But if it does preserve the coloring, then the coloring descends to the quotient, and you get certain eigenfunctions on the quotient that just come from the existence of this coloring. And essentially, you want to ignore these in the analysis. And this is really a higher rank analog of the following. So if you have a q+1 regular graph, you always have q+1 as an eigenvalue, which corresponds to the constant function on the vertices. But if and only if the graph is bipartite, you also have minus q+1 as an eigenvalue, which corresponds to the function, the eigenfunction, where you put a +1 at all the vertices of one color and a -1 at all the vertices of the other color. So that's what the coloring eigenfunction would correspond to in rank 1. Here is a picture of the tempered spectrum and the exceptional locus. So more precisely, the tempered spectrum corresponds to this pink triangle, and the exceptional locus is the union of this brown triangle and this blue triangle. And the theorem says that you need to take a subset of this pink triangle, which has compact and has positive Plancherel measure. And actually, the Plancherel measure is absolutely continuous with respect to the Lebesgue measure of this picture. So really, you're taking, some kind of set like this, which is compact, has positive measure, and doesn't intersect the brown or the blue. So now I want to explain what some of these words I mentioned, the wave propagator, polytopic ball, and how ultimately that reduces the analysis to the so-called geometric bound. So let me go back to the setting of a tree. And imagine I fix a vertex in the tree, say this green vertex, and I pick some half geodesic based at this vertex. Then, so here I can think this is my half geodesic. Then the thing to notice is that the lattice points on this half geodesic exactly parameterize the possible relative positions of vertices from the perspective of green. And this is really just a fancy way of saying that relative position is just classified by distance. So for example, all of these blue vertices in this picture, they look the same from the perspective of the green vertex, namely they're all at distance 2. And you can also think then that the stabilizer of the green vertex actually acts transitively on all of these blue vertices. So I can think of this blue vertex in this picture as kind of a proxy for a sphere of radius 2 centered at the green vertex, for example. And now if I take a polytope, if you will, in this one-dimensional space, which would just be an interval, I can think that the lattice points in this polytope, they're parameterizing basically spheres of different radii centered at this point. And I can put these spheres of different radii together and I can get a ball. So I can think of, in this case, for example, a ball of radius 3 is being made up of 0 sphere, 1 sphere, 2 sphere, 3 sphere. So in this case, I just get a usual metric ball. But what I really want to highlight is that somehow from the data of a polytope in this half geodesic, you got a ball in the building. So let me explain how this works in higher rank. So in PGL3, imagine you fix a vertex in the building and you choose some apartment containing that vertex. Then you can partition the apartment into vial chambers. And these vial chambers are really the higher rank analog of these half geodesics. And the lattice points in one of these vial chambers will actually parameterize the possible relative position of points from the perspective of this green point. And really, this is just like a geometric interpretation of the Cartan decomposition. And we've already seen one instance of this. I said that this green vertex will have neighbors of 2 types, red and blue, but that exactly corresponds to the 2 lattice points in this vial chamber that are adjacent to this green vertex. But if I take some other vertex in this vial chamber, I can think of it as a proxy basically for all vertices that look the same as this orange vertex from the perspective of the green vertex. And so essentially what that means is that I can consider, the orbit of this orange vertex under the stabilizer of the green vertex, and all of those will look the same. And all such orbits will be parameterized by lattice points in this vial chamber. And a bit more geometrically, I can also think that I can reach this orange vertex by taking a path by taking 2 steps along red edges and 3 steps along blue edges. And I consider all points I can reach by taking 2 steps along red edges and 3 steps along blue edges. And that will be the same basically as taking the orbit of this point under the stabilizer of this point. So now if I take a polytope in this vial chamber, I can think, first off, each lattice point in this polytope is giving me something like a spherical shell. And I can put all of these spherical shells together to create some kind of ball. But this ball kind of has a polytopal shape to it because it's coming from a polytope here. And actually, this polytope I've drawn is not arbitrary. In my work, I actually use this specific polytope. It has actually specific, very nice properties that are important in the analysis. So this is not a random polytope. So that's what I mean by polytopal balls. And I can, because in this case, the group is acting transitively on the vertices. If I have a polytopal ball centered at one point, I can translate it to a polytopic ball of the same shape centered at another point via the group action. Okay, so going back to my main theorem, I'm concerned with bounding this sort of expression, and actually the orthogonality of the coloring eigenfunctions in particular implies that you're orthogonal to the constant function, which means that this part here is 0. So I can get rid of this part. So I'm really concerned with bounding this sort of expression, which I can rewrite like this. And what is done is you want to find a certain operator that is very much analogous to a wave propagator, and it will have certain desirable spectral properties that will allow you to relate this expression to an expression of this form. And an expression of this form can be interpreted as computing the Hilbert-Schmidt norm of this operator AM. But Hilbert-Schmidt norms of operators can be computed in two ways. One way is exactly like this expression, where you choose an orthonormal basis and you say how large is the image of each basis vector under my operator AM. But there's another way of computing it, which is by finding a kernel function for your operator and computing the L2 norm of your kernel function. So now actually we're going to compute this expression, or bound this expression, a different way by computing the kernel function and computing the L2 norm of the kernel function. So the kernel function, what does it look like? What is it composed of? Well, this wave propagator, it's composed of pieces that look as follows. You're going to average over a polytopic ball of radius m, by which I mean you take your polytope like on the previous slide, and you dilate it by a factor of m, and you create the associated polytopic ball. Then you're going to multiply by your test function, and then you're going to average over a polytopic ball of radius m again. The kernel function for such an operator will amount to integrating your test function over the intersection of two polytopic balls centered at different vertices. And then at some point in the analysis, under this Benjamin-Schramm convergence assumption, you pass from working on the quotient to working on the building itself with some error that you can control because of Benjamin-Schramm convergence. But the building itself is a homogeneous space. And this intersection of polytopic balls centered at different points, I can think of that as some set in the building, and I can translate that set under the group action, and I'll get a bunch of other polytopic balls intersected at different points. And I need to integrate this test function over sort of all such configurations. And essentially, I can package that information and relate it to instead computing some norm of some convolution operator associated to the shape of this intersection of polytopic balls. And this is where sort of dynamical ideas are coming into play. So there's this ergodic theorem of Neveu that allows one to bound the operator norm of such convolution operators just in terms of the volume of the set defining this convolution operator, and you don't actually need to know the fine geometric information about the shape of the set, which is actually quite remarkable because a lot of different shapes can have the same volume. So this allows one to reduce the analysis to getting a good bound on the volume of this intersection of two polytopic balls, and that's what the geometric bound is concerned with. So now the last thing I want to talk about is how sort of illustrate my approach to the geometric bound by talking about it in the context of the regular tree, where the ideas are a bit more digestible. And so in that context, the setting would be that you take two vertices in the tree, and for concreteness, let's say that their distance apart is 6. And you're going to pick a ball of radius, say, 8 centered at x and radius 8 centered at y, and you look at the intersection, and you're going to get some set. And in this case, the set looks like this. And now this geometric bound would be concerned with computing the volume of the intersection, which is simply counting the number of vertices in the intersection. And I think in the case of a tree, it's not such a hard thing to do, but I want to kind of illustrate the ideas that I'm generalizing in higher rank. And this picture already kind of illustrates some of the ideas, the way that I've drawn the picture. So suppose I have a point in the intersection, call it Z. I can consider the geodesic from X to Z in the tree and the geodesic from Y to Z in the tree. And past some point, these two geodesics will be the same. And the place where they can start to be the same, I'll call that W. It'll be called the confluence point. And the possible confluence points are exactly the different vertices along this geodesic connecting X and Y. And I can use this confluence point to define coordinates for this point Z as follows. I basically ask how many steps along the central geodesic I have to take to reach Z, and then how many points once I branch on this kind of orthogonal branch from the confluence point, how many steps I have to take to reach Z. So for example, in this case, Z would get assigned coordinates 2, 4. So here I've put that at 2, 4, and I can repeat this procedure for every vertex, but a lot of different vertices will receive the same coordinates. So here I've colored all the vertices that get the same coordinates with the same color. And it turns out that the vertices, the possible coordinates that you get for points in this intersection of balls exactly correspond to lattice points in some polytope. And this allows us to convert the geometric bound to the following question. First, we need to figure out an expression for how many vertices receive a given set of coordinates, and then we need to sum up that function over the lattice points in this polytope. So in words, a point Z will get assigned coordinates alpha beta, where alpha is the number of steps along this central geodesic you need to take to reach the confluence point, and beta is the number of steps you take from the confluence point on this kind of orthogonal branch to reach your point Z. And what's important is that the number of points that receive coordinates alpha beta is basically q to the beta if the degree of the tree is q plus 1. And this is essentially because as you move along one of these orthogonal branches, the number of points you reach at each step is growing by a factor of q. And now kind of the Deus Ex Machina tool for the analysis is something called Bruhat's formula, which says the following. It allows you to compute the sum of an exponential function over the lattice points in a polytope, where your exponential function is, its exponent is some linear functional. It allows you to re-express this sum as a weighted sum of the value of the function over the extremal vertices of the polytope. And I want to point out that in our case, because the number of points that receive these coordinates is q to the beta, it's exactly q to some linear functional in the coordinates. So we can use Bruhat's formula to compute this integral, or the volume of this set. And you should think Bruhat's formula, in some sense, it can be viewed as a higher rank generalization of geometric series formula, but it also kind of in the way that I'm using it, it's very much like a polytopal analog of the method of stationary phase. So in particular, it allows you to identify dominating terms for certain expressions. So this formula tells you that the dominating term comes just from the vertex that maximizes this dot product in the exponent. And then I also have some weights here, these coefficients CV. It turns out that what's important, something quite nice about this formula is that these coefficients, they depend on the geometry of the polytope, but they only depend on the local geometry of the polytope at the vertex V and not on the global geometry. So more specifically, they depend on the shape of the cone at this vertex. So going back to this picture, so the first observation is that as the second coordinate increases, the number of points that receive that coordinate is growing exponentially. Then Bruhat's formula tells you that essentially the total number of vertices in this set is of the same order as just the vertex that's contributing the most. And it's also giving you some weight that is depending on just the shape of the cone at that vertex. And what's really important in the way that I'm using Bruhat's formula is that as you vary the distance between X and Y, and you vary the radius of the balls that you're intersecting, this polytope parameterizing these possible coordinates, it changes shape, but locally the shape stays the same. So in particular, for example, the shape of the cone at this extremal vertex is staying the same. And so that allows you to use Bruhat's formula kind of over a whole family of different polytopal balls intersecting. Okay, so the last thing I want to say is something about how these ideas work for PGL3, And really the idea that made all of this machinery work was first identifying this notion of a confluence point. So in higher rank, the thing that's going to play the role of the confluence point is as follows. So first off, in higher rank, instead of working with geodesics between points, I want to work with something a bit more combinatorial, a bit more simplicial, which is what I call parallelograms. So let's say I have 2 points, x and y. I can consider a metric geodesic connecting x and y, but what I'm instead going to consider is the intersection of all apartments that contain x and y, or equivalently, the union of all shortest paths in the one skeleton connecting x and y. And when I do that in this picture, what I get would be this black parallelogram. Hopefully you can see it, but there's this black parallelogram that contains x and y. And now imagine I have a polytopic ball centered at x and a polytopic ball centered at y. I intersect them, and I have some point z, say, kind of out of the page that lies in the intersection. And what I'm going to do is I'm going to consider the parallelogram connecting x and z and the parallelogram connecting y and z. And past some point, these two parallelograms, they will intersect. And the place where they start to intersect, that's going to be the confluence point. So to set up this kind of coordinatization, I first need to understand what these confluence points can even look like. And so one thing that I do is I identify what these confluence points can look like. And this picture shows sort of the most complicated case. So this point W is a possible confluence point, and it has this property that the parallelogram from x to W and the parallelogram from y to W only intersect at W. But anyways, once you identify this notion of confluence points, it allows you to set up this coordinatization for points in the intersection and then reduce your problem to a Brion's formula computation. All right, that's my last slide. Thank you.
Okay, this calls for a round of applause. Thank you, Carsten, for a great, colorful talk. Any questions at all? Comments? Suggestions?
So, so you do this for PGL 3, not, I mean, is there any hope of doing it for higher?
Yes. So yeah, that's sort of actually something I'm actively working on. So yeah, so there's something, so in my analysis, I'm using something special about PGL3. It's really in this geometric bound. And I'm kind of from scratch, like creating this way of parameterizing relative positions, kind of relative to 2 points simultaneously. And kind of after I kind of figured this out, I've found these results in the literature that I can see might allow me to do this in general for, say, arbitrary Bruhat-Tits buildings, but I'm still kind of working out the details. But sort of the only stumbling block to doing this for general Bruhat-Tits buildings is this geometric bound, and there are already kind of quite powerful results in the literature that answer very similar types of questions that arise when doing the geometric bound.
So does it help to take another group of rank 2?
So there's something special. So I thought about the other groups of rank 2. So there's actually something very special about the Weil group of PGL. So I think the product of rank 1 things is easy, or at least a long time ago I had convinced myself that you could do it almost immediately just from the rank 1 case. Even for like irreducible lattices and products of rank 1 things. For the other irreducible rank 2 cases, yeah, there's something very special about the basically the combinatorics of the Weil group that I'm using that doesn't work for the other rank 2 groups. But again, there's certain results in the literature. There's something called Hecke paths, which basically provide a way of parameterizing relative positions of several points simultaneously in buildings, and I think that those ideas could be used to handle this geometric bound in a lot more generality.
Okay, thanks. Other questions? Okay, if not, let's thank Carsten again. virtually or with physical applause.